All right. Thank you very much, David, for the introduction. So I'm really amazed that there are so many people in the vacation time attending this webinar. So 1,600 registered people. Wow. But that tells me also there's a high interest in this topic. And as David pointed out, this is not the first time I am giving a webinar here on this platform. Of course, the topic has always been around hydrogen distribution. So I hope that this time I don't repeat just old stuff, but include some new stuff and new information for you. And yeah, I'm very happy and I welcome you wherever you attend this webinar from. Okay, the structure of this webinar looks as follows. So we have 5 chapters. So the first chapter is I give you a quick overview of Hexagon Purus. Then I continue with some general information on hydrogen storage and distribution. Then I narrow down the topic and then talk about on-road distribution of compressed hydrogen, because this is actually the core of our business model. And then I explain why Type 4 composite distribution systems are on a strong rise. And I conclude with a view on the total cost of ownership, and then you will personally see how this favors Type 4 composite distribution systems. All right. I hope it's big enough for you. So this is Hexagon Purus at a glance. So I start in the upper left corner. We are a Norwegian company headquartered in Oslo in Norway. We are listed at the Oslo Stock Exchange. And the company was established in 2020 as a carve out from Hexagon Composites. Hexagon Composites is a Norwegian company too, also listed at Oslo Stock Exchange, and it is still our major shareholder with 38%. Other key investors of Hexagon Purus are Japanese large conglomerate Mitsui and the hydrogen investment fund Hy24. We count with 650 employees worldwide. And on the map, you see our global footprint. So beside the headquarters in Oslo, we have 2 plants in Germany, one in Kassel in the center of Germany, where I am located, where we produce mainly the Type 4 cylinders, and another plant at the Dutch border in Weeze, which is former company Wüstrach. Maybe for some of you that tells you something. Wüstrach joined the family in 2021. Then we have 4 plants in the US, one in Kelowna in Canada, and then 3 plants in different locations in the US, each one with a dedicated purpose, so assembly or cylinder manufacturing. And then we also count with 2 plants in a joint venture with Chinese company CIMC Enric in China. One is for the production of Type 4 cylinders, and the other one is for system building. Our product range includes Type 4 composite cylinders and systems for the storage and distribution of compressed hydrogen, and also electric drivetrain integration for medium and heavy duty trucks. We now have even our own brand for heavy duty trucks, which is called Tern. This is a business that we only have right now in North America. Which market segments do we serve? We divide our activities into the following market segments. So we have infrastructure, and here we serve then the distribution market with our distribution containers, ground storage market, refueling, and industrial gas market as well. Then mobility, here we offer our fuel tank systems for all kinds of vehicles. On the road, buses, trucks, light commercial vehicles, off-highway vehicles. This includes mining, agriculture, construction. Then we have maritime and rail. In maritime, we are talking here about rather smaller ships and boats, so ferries, supply boats, and so on. And then we have the already mentioned electric drivetrain integration, where we actually take the naked tractor and then integrate either a battery electric drive or a fuel cell electric drive. And we also sell our Type 3 and Type. Here we also still have a few Type 3 cylinders, but mainly Type 4 cylinders then to also aerospace and aviation clients in North America. To the right, you see some of our key customers. And since the topic today is distribution, I mention the most important distribution customers that we have. Among them are all the big gas distributors, Air Liquide, Linde, Air Products, some local and regional ones like German Westphal. And then we have also the newcomers in this business, so the green energy or hydrogen suppliers, companies like Live or Plug Power. Hexagon Purus is a leading provider of storage cylinders and storage systems with Type 4 cylinders. And for those of you who do not know what a Type 4 cylinder is, at the bottom you see that pressure cylinders are classified or into types. So the classical old steel cylinder is a Type 1. Then we have a Type 2 cylinder, which is hoop wrapped. That means you only have an over wrap in the cylindrical part. Then the Type 3 cylinder is a fully wrapped cylinder with either carbon or glass fiber, composite or a mix, and an inner metallic liner. Mostly in our industry, it's an aluminum liner, but it could also be steel, for example, for breathing apparatus. Then Type 4, our specialty, that is a fully over-wrapped cylinder. And instead of a metal liner, we have a polymer liner inside. So the extraordinary properties of Type 4 is that these cylinders are non-corrosive. They have an excellent fatigue strength. And probably the most important advantage is the lightweight. You see how all these different types compare to a Type 1 cylinder. So for Type 4, we are talking about 75% of weight saving against a classical Type 1 steel cylinder. So with this, we can say that they provide a superior combination, of weight, safety, efficiency, and durability for hydrogen applications. And they are the optimal and preferred technology for compressed hydrogen applications. For those of you who do not know how a Type 4 looks like, looks pretty simple, but at the end it's not. There are a lot of details. The blue one is the liner. So two materials are mainly used. It's high density polyethylene, or polyamide. This liner forms the gas barrier. It's not the laminate. And then you have around the liner, you have the carbon or glass fiber reinforced polymer. The composite could also be a mix, but given the high pressure levels and the requirements for weight savings in the hydrogen industry, mostly carbon fiber is used. Then at both ends, you have the metal bosses, which can be of stainless steel or aluminum. They are there to hold the cylinder in a frame and to connect it to a valve or to the piping. Talking about liner technologies, there are 3 liner technologies out there, which is blow molded, which gives you a 1-piece liner. Then we have welded 2- or 3-piece liners where the cylinder is then the cylindrical part is extruded. The domes are injected, and then you weld these parts together. Rotomolding is another technology that gives you a 1-piece liner. Talking about pressure levels, at the bottom you see that also LPG can use Type 4 cylinder technology. Then it's low pressure, 16 bar. In the CNG environment for vehicles, the usual pressure is 200 bar. In the distribution of CNG, 250 bar. Then in hydrogen, for vehicles, we have either 350 or 700 bar for the fuel tank. For distribution, we have now a wider range of pressure levels. So it starts with 300 bar, 380, 500 goes up to 635 bar. And for ground storage, we then reach the highest levels. So usually it starts with 500 bar and can end up at even 1000 bar. So that was the very quick overview of Hexagon Purus. And then I continue with the next chapter. So some really general comments on hydrogen storage and distribution. As you all know, hydrogen is very light gas, smallest molecule on the planet, and it has a very, very low volumetric density at ambient conditions. So you must do something with it in order to efficiently store and distribute the hydrogen. And we can divide these different types into two groups. On the left side, you see the physical based. And here we have compression. Then after compression, you can compress it, or you can compress it into a pressure tank, or you can compress it into a pipeline and then pump it through the pipeline. Or another physical based type is liquefaction. So that gives then the liquid hydrogen. I marked all these types with a blue star just to highlight that these are currently the dominant types, or have been for a while, the dominant types of storing and distributing hydrogen. Then there's cryocompressed, which is a combination of compression and liquefaction. Then we come to the material-based group. Material-based means you need a kind of a carrier material to increase volumetric density of hydrogen. And let's take a look first at the ones with the green star. That's ammonia and methanol. Why do they have the green star? Because they have a special role, because their main purpose has not been to serve as a carrier material for hydrogen. So their main purpose is a different one. That's as a starting material, so a feedstock for other chemical compounds. In the case of ammonia, it's a starting material to then produce fertilizer or explosive or many other chemical compounds. Methanol, it's even more versatile, so it's used as solvent and then also as a feedstock for many, many other chemical compounds. Still, these two materials are mentioned all the time, also when we talk about decarbonization of our planet, because they can play a major role by changing to, for example, green ammonia or green methanol. They have a huge potential for decarbonization, the whole process, how they are produced. Then we have liquid organic hydrogen carrier, in short LOHC. This is a clear carrier for hydrogen. So here as an example, I mentioned dibenzyltoluene as a carrier material. So you bind it chemically first to this carrier material, and then you distribute it, store it, and then you release it again to obtain pure hydrogen again. And I will tell you on one of the next slides a little bit more to that. And then we have kind of a niche product, that's adsorbents and absorbents. The absorbents are the metal hydrides. Here you have kind of a porous, kind of granulate material that you bring into a cylinder. And then through pressure and temperature, you either press the hydrogen into this carrier material, then that's absorption with B, or it adheres to the surface of this material, then it's adsorption. All right, next slide. What you see here is a table that shows the volumetric density that you can achieve from top to the bottom. It increases. So you have a pipeline with the lowest pressure, let's say 80 bar, of course, then this gives a low volumetric density. But in this case, it doesn't play really a role because you pump a huge amount through the pipeline. And then you see different pressure levels for compressed hydrogen. So at 200 bar, it starts with 15 kilograms per cubic meter and up to 1000 bar. Then you end up at almost 51. Then you see LOHC, it's 56. Liquid is 71. And then here I chose two combinations of cryocompressed. And you see cryocompressed increases even further the volumetric density. And then ammonia, that's even higher. And then the highest volumetric densities you can actually achieve with metal hydrides and, for example, MOF5 and adsorbents. So with absorbents and adsorbents. The table also shows you what is the aggregate state of each of these types and what you have to do to convert for conversion and what you have to do to release the hydrogen. Okay, a quick excursion to global hydrogen demand. In 2022, it was 94 million tons of global hydrogen demand. And you see how it is distributed over the planet. So 30% China, then US, Middle East, Europe, India, almost on the same level. And then you have rest of the world. And the column tells you for what it needed. So 45% is for petroleum refinery, then 35% for ammonia, 15% for methanol, and 5% for steel or maybe other industries. And in the text, you can see for what other industries it's actually used. So it's really glass, plastics, food, chemicals, pharmaceuticals, semiconductors, and so on. Here we look at the hydrogen production, and 90% of all hydrogen production is actually internally consumed. What does this mean, internally consumed? So this is on-site or nearby production for large consumption. So if you think of a methanol or ammonia or a refinery plant, then they have such a high need that it doesn't make sense to transport and distribute these large amounts of required hydrogen. So you produce them on-site and consume them immediately. And only 10% is merchant hydrogen. So that's the one that is then distributed to other clients and end users. Almost all of this hydrogen production is still gray. That means it's still produced with predominantly steam methane reforming and emits huge amounts of CO2. Only a very small portion is green, but yeah, that's what shall change in the next decades. All right, then we see also a different picture in the US and in Europe. So I just took these two regions as an example because there's vast information available. Starting on the left side, what we see is really a high concentration of production sites in the US and larger production sites. And we also see that less than 1.5% of all produced hydrogen is actually distributed on the road. So that's not much. But that explains why a lot of hydrogen is immediately used on site. In Europe, the picture is a little bit different. So we have many more production sites, smaller ones dispersed over the continent, but we have a similar picture when it comes to road distribution. Less than 2% is distributed over the roads. In the US, we have more liquefaction plants. So talking about now the relation between liquid and gases. So, and in Europe, we have only 4 liquefaction plants. Right now, there are being added liquefaction plants in both regions, but not many. Okay, this is really small quantities. And what is really interesting is that in the US, 85% of the trucked hydrogen is done in form of liquid hydrogen, and in Europe, it's only 5%. Well, that's a big difference between the two regions. Why is that so? Well, in the US, you have larger distances, you have lower energy costs. That because liquefaction is very energy intensive, you have lower fuel costs, and that explains why the picture is so different. Okay, now I go into more details to each of these types of hydrogen storage. Compressed hydrogen in pressure tanks. This is used actually since the end of the 19th century, but larger quantities started really in the 30s, last century, after the introduction of steam methane reforming. Still, steamless steel cylinders type 1 are the dominant technology. They are used in bundles, stationary storage, tube trailers, but composite technology type 4 is on the rise in road distribution. So this started about 10 years ago. It's, given the history, a mature technology, and it's currently the technology of choice for hydrogen projects with small demand and shorter distances. And also the investments are limited. If you think of a value chain, compressed, you spend for the distribution systems, and then you have the compression upstream, and then downstream you have the reduction. Then the overall investment is compared to liquefaction, for example, limited. Energy demand for compression, so for mid size pressure, so 300, 350 bar, it's 3 to 4 kilowatt hours per kilogram. If you compress to 700 bar, it's 6 kilowatt hours per kilogram. If you go up to 1000 bar, then we talk 8, 9 kilowatt hours per kilogram. At the bottom, you see the evolution from just one cylinder over a bundle to type 1 tube trailer, and then to type 4 multi-element gas container. More than to that then later. So you see how the payload actually increased from left to the right. Then pipeline. So of course, pipeline main distribution is the purpose is distribution, not storage. The first pipelines for hydrogen were actually built in Germany in the beginning of the 30s. Worldwide, there are about 4,500 kilometers of pipelines, which is tiny compared to oil or natural gas pipelines, but they exist. Okay, mainly in Europe and US, half, and a little bit in Asia. They are, of course, the preferred choice for large industrial consumers, and pressures can go up to until 85 bar. And there are actually new pipeline networks planned, and they plan to convert natural gas pipelines and build new ones. And as one example, Europe has plans to build a European backbone of approximately 30,000 kilometers until 2030. And about 60% should be converted pipelines and 40% new ones. If you look at the throughput of such a pipeline, that's amazing. Here, just an example. If you have a 1 meter diameter pipeline and the velocity of 15 meters per second and at 85 bar, at full utilization, you can actually distribute 300 tons per hour. Oh, that's really amazing. The investments are, of course, high, but it really depends on the pipeline itself, the environment, the topography. It can be $1 to $4 million per kilometer, or even a little bit more. Conversion of gas pipelines, however, is much cheaper. So I read this information, $0.2 to $0.6 million per kilometer for this European backbone. Then liquid hydrogen. So the first liquefaction in large scale, talking about large scale, was done in the US in the 50s, of course, for NASA, for aerospace application. Today, worldwide, we can say that the commercial production sites are spread as follows: 15 in North America, approximately, Europe 4 to 6, Asia approximately 15 to 20, so most of them in China and in India. They have common output of 0.2 to 30 tons a day, but to make them even more economic, it's said that they should increase to 50, 100 tons per day. And then the distribution happens with liquid tanker vehicles, which then have a payload of 3,500 to 4,500 kilograms. And here the negative thing, the investments in liquefaction plants is huge. So in Europe, for a 10 ton per day plant, they spend 60 million euros, and in the US for a 27 tons per day plant, they spend 150 million US dollars. And it's energy intensive, and that's expensive, so it requires 10 to 15 kilowatt hours per kilogram. If the bigger the output per day is, the more you get down with these costs. So if you have 100 tons per day, then you can achieve lower energy consumption per kilogram. This is roughly, as it is written here, a third of the energy content of hydrogen, which is 33 kilowatt hours. And you still have to deal with the boil-off topic. Okay, then cryocompressed. So that is at a very early stage. So and it's rather for onboard storage of vehicles, airplanes, for example, where the higher density compared to the liquid really justifies a business case. We will see what the future role of cryocompressed will be. Now we talk about the material-based ones. Ammonia and methanol both have a long history of more than 100 years. So large-scale production of both started in the 20s. And the annual production of ammonia is really impressive, 170 million tons. Also, the number of methanol is impressive, 100 million tons every year. Ammonia production uses mainly gray hydrogen, so therefore it emits a lot, 1.4% of global CO2 emission. So there's a huge potential for green or blue ammonia if then the CO2 is stored underground. And ammonia becomes interesting. So there's a huge potential to get ammonia for its original purpose, green, that is using it as a feedstock. But there's also a potential to use it, for example, as a fuel in large container ships, for example. Yeah, so ammonia can actually be burned in large engines, and that makes it interesting. It's flammable and it can explode when it's warmed up, and it's toxic when you inhale it. Methanol is a different story, right? It's a complex compound with so different applications and also the different ways of producing it. There's a potential to also decarbonize the production of methanol. Okay, but the overall carbon footprint of methanol really depends on how it is produced and how it is used at the end. So here you have to really to look at the whole value chain or the whole process to be able to say, okay, here we have carbon neutral constellation, or here we emit carbon dioxide, or here we have by using green methanol even emission-free application. And methanol is a flammable liquid. Then I go directly to LOHC. That's at an very early stage. So the first commercial plant was built in 2016, I believe, in Germany, at least in Europe, I believe. And in Asia, there's another one as well, rather small demo plants. But it's an interesting type. The main target for this is really industrial off-takers. However, there are further studies and developments to use it directly or indirectly in fuel cells on boats, for example. I told you already that this is a clear hydrogen carrier. Okay, so and as an example, here I show you what it takes to bind it. It's called hydrogenate it to the carrier material, and what it takes to dehydrogenate to release it from the carrier material. So it gains heat when you hydrogenate it, and it requires heat or energy when you release it. So this explains why this is interesting for industrial off-takers. So if you achieve or succeed in using the generated heat, or if free heat is available for the dehydrogenation, then this becomes really interesting. What does it also make an interesting material is that it's no dangerous good when it's transported. So, and you don't need any pressure or any cooling. So that is really charming. A disadvantage is you have a circular logistics for the carrier material. So when you dehydrogenate, the carrier material goes back for a new hydrogenation circle. Then absorbents and adsorbents. So there's no widespread use so far. They have the highest storage densities without any doubt, but there are several challenges to overcome, which are weight, costs, slow gas fill and release. Therefore, today, they just see some niche application, for example, military submarine or in boats. But further applications are here under study, for example, as a ground storage. This was the general excursion to hydrogen storage and distribution. And now I come to the on-road distribution of compressed hydrogen. Oh, Jesus. I was too quick because I wanted to open a poll here. Yeah, I believe I ruined the poll, but still, let's see it. I don't see the poll here on in my menu. Well, then I cannot. Well, then we skip the poll. Sorry for that. I just wanted to ask you, when do you think that on-road distribution for compressed gases was actually introduced? And yeah, so, but I was too quick with the slide, and therefore I go directly to this slide. It's really an interesting slide, I believe. I stumbled over it when I did some research on the internet on history of distribution of gases. It actually shows a distribution system more than 150 years ago in Paris, and it is for the transportation of coal gas. So, and if you compare the concept to the left and with the concept of today, well, you have to say that this concept has been around for a while now. Okay, coal gas was used to lighten streets and buildings and for cooking in the 19th century, because before it was then actually then later replaced by electricity and natural gas. Yeah. There's another copper engravement on the same topic. You see the same cylinders. This is probably a refueling station for coal gas. Look at the technology of the cylinder. So this is a cylinder, not a seamless steel cylinder. It's made of steel sheet riveted together. Pressure levels here were usually in the range of below 20 bar. And you see the guy operating the pump. So he's the living compressor. Yeah, that was a technology 150 years ago for coal gas. So this was some fun fact. Talking about history of hydrogen distribution, a really first milestone we saw in 1884 and 85 when seamless steel tubes were introduced. And with them then also short afterwards, seamless steel cylinders. This was the birth of industrial gas business, because then it was the first time it was possible to store and distribute large amounts at 150 bar. In the 30s, we saw the first steam methane reforming, which was then the start of large-scale hydrogen production. Before, it was coal gasification was used. And also we saw the first pipeline in Germany. In the 50s and 60s, we have two milestones. One was improvements in steel alloys, what then led to an increase of pressure levels for the storage to 200 and 250 bar on steel cylinders. And we also saw the introduction of liquefaction for liquid hydrogen. In the 60s, then we saw the introduction of type 3 and type 4 cylinders in the aerospace and aviation industry. And then we come to the commercial use of type 4 technology, and it started in 92, and it was a retrofit car for CNG, 200 bar. And then in 2006, we saw the introduction of type 4 technology in CNG distribution in the US, 250 bar. And for hydrogen, it started then in 2012 with a 500 bar vehicle for German customer Linde, and in 2014 then a type 4 with 300 bar, which then defined a new industry standard. So going away from the 200 and 250 bar steel trailers to 300 bar composite containers. In 2021 we saw a new composite standard coming up for distribution cylinders. With this, it was possible to increase even further the pressure levels. And today in the yellow circle, we see a strong rise of type 4 and in distribution, and pressure levels from 300 up to 635 bar. Sorry. So here I would like just to explain you a little bit some denomination. Okay, on top, for example, you see 2 containers, right? This is a container design. What does it mean? You can lift the container from the semi-trailer underneath. So, and in Europe, this is even written in our regulation. This is called multi-element gas container, or in short, MEC-C. That's really an expression that is widely used in Europe. The bottom, however, that is a battery vehicle design. Strange name, has nothing to do with electrical battery, but that's how it is called. And here the upper structure cannot be removed from the semi-trailer underneath, so it forms one unit. The advantage of a battery vehicle is that you have more space available and you have some weight savings because a frame weighs something. But the advantage of the container design is you are super flexible, because when you have to do maintenance repair on the semi-trailer, then you just lift the container off, put it on a new one, and then you continue your operation. That's not the case with a battery vehicle, because for that, if you bring it into a workshop, you need a special workshop that can handle this kind of dangerous good trailers or battery vehicles. The weight saving is very important for the battery vehicles, because since they are of steel, and we talk about type 1, they immediately reach the 40 tons maximum gross vehicle weight in Europe, which is the standard in most European countries. Some countries have higher gross vehicle weights, so it's 44 in the UK, for example. Scandinavia can go up to 50 tons. But in most countries in Europe, you have to stick to the 40 tons. So please keep this in mind, because very often expressions are confused. A container is a container, a battery vehicle is a battery vehicle. They are from the design different. And by the way, in the US, they use a different expression. They use trailer, which explains more what this is, a battery vehicle. And but very often you just hear people talk trailer, and they use it for everything. But strictly speaking, it's not entirely correct. All right, then I give you an overview of the Type 4 distribution systems that Hexagon introduced in 2012. Hopefully it's not too small. So the modular design now of the frame is in the 7th generation. You see segments which are bolted together, frame segments, and they are used for all the sizes from 10 to 45 foot. So we have an equal parts strategy. We use corrosion protection, either zinc plating or powder coating for the frame. We use stainless steel piping on top, cabinet at the rear end, and lateral tarpaulins with print for weight reasons. The container is either an ISO container or 255 width. That's the maximum you can use in Europe. They fit onto a standard semi-trailer chassis, and the total vehicle height is 4 meters. We use the vertically mounted cylinder concept. More to that on next slide. Because in Europe you have also limitation in cylinder size, which is 3,000 liters or 1,000 bar liter volume. That means if you have a 500 bar cylinder or tube, it cannot be larger than 2,000 liters. Then we use our Type 4 cylinders. Let me go quickly to safety. So safety is very important. And of course, all these containers, they follow standards. ADR is the European standard for dangerous goods on roads. RID and ADN, it should be ADN, is for rail and inland waterways. And then you see cylinder standards. So we are under the constant surveillance of notified bodies. Then every single cylinder is tested before it is delivered. We have destructive batch testing, which is mandatory, and we have mandatory periodic inspection every 5 or 10 years with cylinder testing. Then, of course, the container is equipped with safety features like open design for venting in case of leakage, pneumatic section valves for remote shutdown, thermal pressure relief devices to vent the system in case of fire, residual pressure switches to protect Type 4 cylinders from falling below certain threshold pressure. Then we use state-of-the-art components and whenever orbital wells instead of compression fittings and emergency stops and so on. So now some words to the mounting options. Here you see three basic mounting options. The upper left is not allowed in Europe given this limit I just mentioned. So what you see is the horizontal in the upper right corner, usually 6 meter long tubes that is available that fits into a 20-foot container, or if you use them back to back, then in a 40-foot container. But with one tube, you are not flexible. You can only then have 20 and 40 foot. So the predominant technology in Europe is actually what you see in the lower left corner. That is smaller Type 4 cylinders in vertical mounting. What are the advantages of this vertical mounting? First, you have one cylinder that really fits to all container sizes from 10 up to 45 foot. And yes, we have many clients who order smaller units, 20, 30 foot, not just the big ones. Smaller cylinders have an advantage. They are easier in the handling. They have lower development and homologation costs. The development is faster. You have a better serviceability in the field when you have to take out a cylinder, and they have a much lower energy content just in case a cylinder bursts, something that in our case has never happened. And then something that is not so publicly known, they have a much faster filling and unloading behavior, which is 2 to 4 times faster than the long tubes because of the thinner wall thickness and the more overall surface in one container. They have a superior total cost of ownership due to this. Faster fill and faster unloading compared to large tubes. And we have piping on top, so that means in the case of leakages, direct venting upwards into the atmosphere. The disadvantages are there as well. So we have more cylinders, that means more complexity, more leakage spots, higher system costs due to this higher complexity, and also smaller cylinders usually have a higher cost per kilogram of stored hydrogen. This leads then overall to a higher purchasing price. So now I come to the rise of Type 4 distribution systems. It's just one slide. You learned now a lot about Type 4 and Type 1 and how they compare to each other. So Type 4 have 3 times or even 4 times more payload than Type 1. You have higher pressure levels. And this is also favored and well seen by specifically the mobility clients, because for refueling, it's better to arrive with more pressure than with low pressure in the distribution systems. Type 4 exists in all sizes, so it's very flexible, and our clients appreciate this very much. Yes, Type 4 are about 3 times more expensive in absolute, no doubt about that, because carbon fiber and composite costs money. But then compared on a per kilogram of hydrogen basis, it's almost on the same level. If you look at the service lifetime, it's the same. So they have the equal service lifetime. Our clients target usually 30 years, but if they are treated well and if periodic inspection yields positive results, you can use them even longer. Most use cases, and this you will see then when I come to total cost of ownership, speak in favor of Type 4 due to the higher payload. That is really here the game changer. Then before Type 4 was introduced, so 10 years ago roughly, there was an estimated fleet of about 800 to 1,000 Type 1 trailers for hydrogen on the road in Europe to serve industrial clients. So this Type 1 fleet is now being replaced by Type 4 systems, of course, due to this superior TCO and also for mobility clients, for the upcoming mobility clients. So these mobility clients are now being added to the complete, let's say, customer base. Since 2012, our estimate is that all competitors together, we are not alone in this world, about 450 Type 4 systems have been brought into the market in Europe. That's within 10 years or 12 years, a very nice number. Okay, and now I come to total cost of ownership, the last slides. Total cost of ownership is always in logistics the superior model to look at costs. You just do not look at the upfront cost, that is the purchasing price of an asset, but you look at all the costs that you have over the service lifetime of an asset. In this case, we look at 30 years service lifetime. In our case, in our model, we include the tractor and the semi-trailer underneath into the model. However, compression and reduction, so upstream and downstream, that is not included in our model. The outcome of this model is, of course, cost per distributed kilogram of hydrogen. I emphasize here it's cost, it's not price. So we do not estimate or include any overhead or any profit margin here. And of course, there are countless variables, not countless, but a huge number of variables that you put into such a model. So you have, of course, all the CapEx numbers. You have all the OpEx numbers, like how much the fuel costs, how much a driver costs, inspection, maintenance, insurance, etc., etc. You have the operating mode. Does the container remain at the station, for example, to be emptied, or do you dump it there? And then when you do this kind of TCO, you come always to the two dominant variables that really change the output of the TCO of the cost per distributed kilogram of hydrogen, and that is the consumption per day and the distance to cover between the production side and the use side. And then you throw everything into this model and you shake it, you massage it, and then at the end it spits valuable data out, and then it's up to you what you do with the data, and there are several forms to use this data. Okay, and here this is one classical chart. You see on the x-axis the distance to cover, on the y-axis the consumption in kilograms of hydrogen per day, and you see there's really not a big area left for Type 1. A much larger area is left for Type 4 carbon fiber systems, distribution systems, and then also for liquid. There is a large area where the combination of distance and consumption really speaks in favor of one or the other technology. Of course, this follows a logic, right? I have not expected something different, but still, it proves, you know, that the logic. Another possibility of using the data that the model spits out is this one. Here we chose three definite use cases: 300 kilograms consumption per day, 1,000 and 4,000 kilograms a day. And then we have here the distance on the x-axis, and here we have then the cost. Here it is in $1,000 per ton. If you divide this by 1,000, then you have it in dollars per kilogram. And if we start on the left side, this is a low consumption, then you see Type 1, yeah, it's still, that's the white line, by the way. Yellow is the Type 4 composite and blue is the liquid. You see there's a small operating window that still favors the use of Type 1 at very short distances below 50 kilometers. But then when the distance gets bigger, you see here the change of color from green to dark green, then liquid wins over the Type 4. And if you go then more to the right, and let's look at the 4,000 kilograms a day, you see there's no use case at all for type 1 anymore, completely out from the beginning. And then you see that at the shorter distance already, liquid surpasses type 4. So that's another way of using the output data of such a model. A third possibility is this one. Here we just choose one system, 40 food, 380 bar, 950 kilograms of nominal payload, and Germany. Means German costs, German fuel costs, German drivers costs, and so on. And here we use pure costs. Distribution system, tractor and semi-trailer are owned, not financed, no leasing or whatever, no overhead, no margins. And we use the equipment absolutely 100% efficiently, no idle time, no standing around. Okay, and then you see here again on the y-axis the kilometers, on the x-axis then the consumption. And I try to visualize then it better by using different colors. So below 50 cents, it's green. Between 1 and 50 cents, €1.50, it's yellow. And then between, I believe, 2 and 1, it's red. And gray is above 2. And this is a remarkable chart because it tells you the following. There's already, how can we read it? It means the higher the consumption is, the lower the costs get. And the shorter the distances are, the same applies, the lower the costs get. So from lower left to the upper right, we then see the costs drop considerably. And this is interesting because there's an inherent cost reduction potential due to mass penetration and efficient logistics of hydrogen. So we only need larger demand and we need more mass penetration of hydrogen, and then this automatically drives down costs. It's very funny, very interesting. Okay, but of course there are even there's more potential to get down costs because it also means you can get costs down if you have more consumption, shorter distances, or more modules in the market. Then of course we as a company, as an equipment manufacturer, we also then have economies of scale in our production, better fixed cost allocation, and so on. Yeah, that was total cost of ownership. And with this, I come to the last slide and a summary. So what is the future of compressed hydrogen distribution by truck? So type 4 will become the predominant technology for on-road distribution of compressed hydrogen, and it will replace type 1 and the other technologies as well. That is type 2 and type 3. And they are and remain ideal for small and medium consumption at short and medium distances. And compressed or gases, which is the same, will not compete with liquid pipeline, LOHC, ammonia, and methanol for large quantities, large industries, for example, and for long distances. For example, sea transport, because you cannot fool TCO. So customers will always look for the highest efficiency. And you also know that the build of new liquefaction plants will take time, especially in Europe. So there might come up competition with liquid hydrogen on the road as well, but it will take time. In the US, it's a complete scenario, as you learned. The same applies to build of pipeline network. That will take time to develop. And as you heard, that's only, in brackets, a backbone plant. A backbone can even seem positive for our business because it opens opportunities for trucked hydrogen to cover the last mile. Of course, last mile here is not just 1 mile, it's maybe 50, 100, 150 kilometers, because there will be consumers that are not close to the backbone. Technologically, what can we say? The payload has almost come to a physical limit with compressed hydrogen distribution, but we still can improve further safety and reliability because the more hydrogen is distributed on the road, the higher is the probability of an accident. And accidents will happen. And if they happen, then we must have as much safety features included as possible in order to minimize the consequences of such an accident. Digitalization is a big thing. So smart functions like hydrogen detection, health monitoring of cylinders and systems is something all the players are working on. Then we would like to facilitate periodic inspection and hydrogen purging in order to reduce downtime and costs in the future for the periodic inspection. And of course, CO2, lower the CO2 footprint of Type 4 cylinder production and systems. Buzzword here is green cylinders and green systems, because the system itself has still a certain CO2 footprint in the production. And then, of course, improve costs further down. That is something that I just mentioned. All right, this was the last slide. And now I have, let's see whether the poll works. I can't see the poll, sorry for that. But this was, then I finished.
It's there, it's there. People.
Yeah, but I cannot see it.
On the right-hand side, if you open where the chat is, you just have to click on it. So people, you have to open the chat. There it is. The other one was there as well. Sorry, I didn't want to interrupt you.
Yeah.
Okay. So you see the result?
No, I don't.
Okay, so let me read it. So 2050, 44%, 43, 2075, 37, 2100, 13, after 2100, 7%. So most people are optimistic for 2050.
Can you say it again?
So the question is, I mean, you know that when do you think the world will have changed to a large extent from fossil to renewables? 2050, 44%, 2075, 35%, 2100, 12%, after 2100, 6%.
Oh, that's
people are optimistic.
More optimistic than I thought, right? Okay. Then questions and answers.
Yes, thank you very much, Hartmut, for this presentation. So let's give him a virtual round of applause in the chat. I promise you a fantastic presentation, and I saw it in the chat already. Most people agreed, and I will award you 3 Olympic medals today. In the chat, where are they? Looks either they have disappeared or they're, you see. I hope you have opened the chat now. I will award you another medal just to be sure. Standing ovations. Just look at the chat. Absolutely amazing presentation. Thank you very, very much. Or should I say, it was a presentation as expected.
Yeah, you announced it highly, so
yeah,
I was not sure whether I can meet the expectations.
Look at the chat.
Thank you very much. I'm really.
So I would say
really very nice.
I would say it was worth to skip my grandmother's 99th birthday and meet her tomorrow instead of today to be here for you. And with you. All right, so let's that was the good let's say the good part. The bad part is we have so many questions, we will not make them not be able to answer them all. Maybe to the team, maybe you can increase the size of the picture of our pictures again, so people can see us, and just in case you think I'm sweating, it's not because of the questions or the presentation. It's we have 33. I have 33 degrees here in my office because the air conditioning is failing again. Okay, 1,300 kilograms of hydrogen at what pressure? So that's 500 bar or 350? 380?
No, then we really go up to 635 bar.
Okay. Okay, and what's the maximum capacity at 380, which is, as far as I can see, the most common pressure at the moment?
Yeah, in a 45-foot container, it's about 1,200 and between 1200 and 1250. So
Okay, more or less.
Yeah.
Okay. If you have, if a customer approaches you with a request for, let's say, a 20-foot container, or something with 300 bar, would you recommend to get, a big system right now, just to be prepared, and to avoid stranded assets long term? Or would you recommend to buy something small today and to buy something bigger tomorrow?
Very interesting question, and very valuable question. And I asked our clients the same. We have clients who today buy many 20-foot systems. And I asked them, well, have you thought about what's happening in 10 years? And then they say, well, when you have more demand, then TCO would speak always in favor of larger systems. With a 20-foot, it's easy because you can put two 20-foot on one 40-foot. It's not so ideal because then you have two connections.
Yeah.
But there's no clear answer, right? Because if you buy 20-foot today, you might be fine for some years, and then it might be too small in the future.
Yes.
If you buy 40-foot today, it might be too big now, but in some years it might be the perfect fit. We leave this decision up to the clients.
Okay. Yeah, it's and I mean, same with the pressure. I see many customers going for a 380 bar at the moment. I can understand the reasons. I can understand, why they believe in 380. My personal recommendation is always to go for 500. Yes, the capacity is a little bit bigger, the cost is somewhat higher, but if you look at it from not only from a transportation and distribution perspective, but also if you use the pressure, for example, at a refueling station, you can fill more cars just because you have more pressure. So the pressure is valuable as well, not only the mass. So that's why I prefer to design everything to 500 bar. Yes, it's more expensive today, but long term, what do you think?
Well, I can tell you what our customers currently buy. Okay, we see, I would say 55 to 60% 380 bar.
Okay.
I see 40%, 45% 300 bar, and I see then 5% 500 bar.
Only 5%.
Right. The main reason is really it hasn't so much to do with the distribution system itself and the cost. It's of course much more expensive. It has to do with the infrastructure around, particularly with compression. So we have clients that say compression is still not, I don't know, good enough support. Maybe you have a different opinion. I only repeat what clients tell us.
No, I don't.
That's the fact today. Okay.
Yeah.
We expect pressure level to increase over the next years so that 300 bar will get smaller and smaller, and customers will go with 300, and 500 bar will increase as well.
Look, I mean, I don't have it on the slides now, but this is the plant, or one of the plants that we have built in Switzerland. It's actually this is one of your hydrogen trailers, which is the customer of our customer in this case.
Yeah.
And I mean, it's just you and me and our 1,000 something best friends now. So I will share a secret with you. We have designed everything for 500 bar.
Yeah.
All the trailer filling station, everything was prepared for 500 bar. And then our customer found out, well, they knew it before, but it was confirmed during the project that none of their customers is currently operating 500 bar trailers. So we had to downgrade the whole thing to 380 or 300 bar. But we can increase the pressure very quickly. So as soon as they have a customer for 500 bar, they just have to adapt a few things. And yes, other people design filling stations for 300 or 380 bar. and they will have to replace the whole equipment.
Yes.
Which
Mm-hmm.
is also some sort of a chicken and egg situation.
Yes.
You have to invest in a new compressor, which from my perspective doesn't make sense.
Mm-hmm.
Okay, so
yeah.
I think we're on the same page here. We have some requests if people can get your contact data. Hopefully to buy or to get more information. Maybe your private email or private phone number would be.
I type it. Just typing it.
Okay. Can you share a few words on hydrogen embrittlement and materials?
Yes. Do you see my email now? Not sure. Yeah, there it is. Okay. Hydrogen embrittlement is not something that happens on polymer liners. That is something that happens only with metal liners.
Yes. Or with pipes and valves.
Yeah, with pipes.
Safety systems.
I have to be honest, I don't know all the answers, right? I'm not an expert in metal liners. I'm not an expert in hydrogen embrittlement, in pipelines and in type 3 or in steel cylinders. What I can say, I mean, let's be honest, steel cylinders have been around for a while, okay, for more than 100 years, how you learned today. They are used for even up to 1,000 bar for stationary storage at refueling stations. I know that when it comes to cycle fatigue, composite in combination with polymer liner, they have better behavior, but still the steel cylinders have improved so much that in all fairness, we have to say that if there was a problem with hydrogen embrittlement, nobody would actually buy those cylinders, right?
Yes. Of course. So, but you, I mean, it's fair enough to say that you're not an expert for those materials, but all the pipes and everything you use is made from stainless steel, I would assume.
Yes. Everything that is in contact with gas is stainless steel.
Okay, good. Good. So before we can continue with the questions, let me announce the webinar on hydrogen in Taiwan. I'm really looking forward to that. So let me just read from my second screen what you're going to learn there. Hydrogen development in Taiwan's net zero emission roadmap, probably with tube trailers as well. Power generation from semiconductor industrial byproduct hydrogen. Taipower's gas-fired hydrogen blending for power generation demonstration project. ITRI's hydrogen-powered drones and AEM hydrogen electrolyzer technology. CPC Corporation's hydrogen refueling station construction and bus demonstration project. Taiwan's hydrogen industry and internal cooperation with Delta Electronics with SOEC hydrogen production and Bloom Energy's SOFC power supply system. Guys, is that amazing? Hydrogen in Taiwan in 3 weeks from now, and SOECs are in 4 weeks. So please register for those webinars as well. So next question on filling speed, or we all know, and we have worked on that as well for many years. If you fill them quickly, it gets hot in the tank. If you empty them too fast, it gets cold, or maybe even too cold. Can you share a few words on that? Because as experts know, the temperature and distribution system, the maximum temperature is only 65 degrees, not 85 degrees.
Right.
Do you see that as a problem?
Yeah, it can. Question is it a problem? But it can slow down either the filling time, or it can really limit you then in the how's it called, the actual quantity of hydrogen you can put into the system. In Europe, according to the standards, so the operation temperature is between minus 40 degrees and plus 65 degrees. Although, to be honest, the cylinder itself, the Type 4 cylinder, could withstand more. For example, the same Type 4 cylinders in the automotive applications goes up to 85 degrees. So we have here something in the standard that, okay, this limit is maybe too low. But yes, if you have 30 degrees, 40 degrees outside temperature, right? You do not cool the gas when you fill a system, then you can really easily reach the plus 65 degrees. So this means, what do you have to do? Either you cool it down or you fill very slow, or when you reach a 65 degrees, you stop, let it cool, and then continue, or you just stop and drive with less. So this, and the same in wintertime when you unload in let's say Scandinavia, minus 30 degrees. Yes, if you unload very quickly, you can very quickly reach the minus 40 degrees, and then applies the same. You stop, okay, or you just slow down the unloading rate.
I mean, that sounds reasonable, but honestly speaking, it's not because it's very inefficient to just drive with less, or to just stop because I mean, look, I'm an engineer, and you know that, and we have developed lots of systems where these cylinders or these systems are used for stationary storage as well, or where the distribution system is also part of of the refueling station, and you can't stop the refueling just because the hydrogen is the temperature is too low in the tank system. So you need more tank systems, which makes it very expensive. So I think this is a big problem, actually, especially, or what we have found out is that the low temperature is even more challenging, because it takes so long to warm up that gas on the inside. It's not easy. But wouldn't it be allowed or possible to say, okay, we fill you design everything to 85, but you have to wait until you're, I don't know, below 65 until you hit the road again. So you know what I mean?
Yes. Yeah. We actually allow our customers to fill short term to higher temperatures.
Okay.
Because the 65 degrees, they refer to the temperature of the cylinder itself, not to the gas. So we have clients that actually fill to maybe 70, 75 degrees, and then they stop, okay, because then the temperature drops relatively quickly, and then when they are down to 65 degrees, then they can hit the road. Yeah.
Okay, so in the filling process, it's allowed to be a little bit higher.
Yes.
Because in the automotive standard, actually the gas temperature is what counts, but
yes.
in the ADR, it's the wall.
It's the cylinder itself, right?
Yeah. Okay, but tell me the temperature.
Yes.
The liner temperature on
top.
It's
absolutely right. It's a gray zone. And also because you do not measure, I mean, we have temperature sensors inside, but they measure the temperature of the gas, but not the temperature of the cylinder.
Of the wall, yeah.
There's no way to do that. I mean, there is a way, but we don't do it.
Yeah.
Okay? So there is some, I would say some, buffer.
Gray zone, okay.
Yeah, gray zone buffer, okay. Because the cylinder itself does not get damaged when you go to, higher temperature. Of course, you should not go to 100, 120, right?
Interesting comment. I hope we can write that down somewhere in the minutes of and refer to it in a case of legal battles. I can tell you. I mean, it's an open secret. It was published, or it was shown in standardization committees 12 years ago. We did a project with an OEM, actually with your cylinders, and we have filled those vessels, we have preheated the vessels to 50 degrees and to 65 degrees. And we filled them in 3 minutes with gas that was preheated to 65 degrees as well. So not ambient temperature, preheated gas.
Yeah.
So the maximum gas temperature was around 150, 160 degrees after those 3 minutes. And we did that 50 times. And then we analyzed the tests. We did burst tests with these vessels, and nothing happened. So no damage at all, even at those temperatures.
I see there are so many interesting questions. Can I select?
Please go ahead.
Okay. Can Type 4 cylinders be requalified at the end of the fatigue life or must be disposed? Well, we qualify all our cylinders to non-limited lifetime. And that's really true. Non-limited lifetime. Of course, every 10 years, we do a periodic inspection. And with this periodic inspection, we find out whether the cylinder is good for the next 10 years.
Okay.
So it's non-limited lifetime.
But tell me again, this periodic inspection is just you just open it, you look inside, or what
okay,
type of
right
test
now in Europe, the periodic inspection consists of the following. You have to take the cylinder out of the system, disassemble everything, bring the cylinder into a test facility, or it can be our test facility, and then you do hydraulic proof pressure test, so with water. Then you have the visual inspection outside, inside with endoscopy. Then you have the leakage test at working pressure. That's the current test procedure. The industry doesn't like it so much, so the industry is working on something different.
Something
because nobody cheaper. Well, what is not liked are two things. First, that the systems have to be disassembled completely, so there's a long downtime, of 4-6 weeks. Yeah, nobody likes, because what do you do during the downtime? And the hydraulic proof pressure test brings water into the cylinder. Water with hydrogen is not a good idea. We want to get rid of this moisture in the Type 4 cylinders.
Yes, of course. That's a big issue. Yes.
What else?
Okay.
What is the gas loss during storage? Well, we have natural permeation of Type 4 cylinders. There's no gas loss like a boil off, but the natural permeation is extremely low. It's in the really 0.0 something percentage. I'm not sure. Of course, it depends on pressure level, whether you have a thick wall, a slim wall, then the standard, and the size of the cylinder. But I don't have the exact number. But if you fill a cylinder and leave it there for 1 year, then probably it's one-digit percent that you would lose as permeation. And on per day, it's 0.0 something percentage. So we call it as negligible.
Yeah, it's a few molecules that you use, lose. And okay, where's that plant in Canada? Let me go ahead. Well, you might select the second one.
That is Kelowna, at the west, in southwest of Canada.
Okay.
That plant does just the drivetrain integration.
Okay. But the main plant for cylinders is in Lincoln, Nebraska. Still.
No. That is now in Westminster, in Maryland. Yeah.
All right.
In Lincoln, Nebraska, they now do CNG cylinders only there. So we split some years ago. We split our activities into CNG and hydrogen.
Yes.
Hydrogen became Hexagon Purus.
Yes.
Plus the electric drivetrain integration, and all related to CNG, biogas, renewable gas, that is today called Hexagon Agility.
Yeah.
Okay.
But there is no hydrogen activity in Nebraska anymore.
No.
Okay. I wasn't aware of that.
Right.
Okay, so let's go.
How does a Type 4 cylinder perform in a crash test in terms of safety? Well, it probably depends on the crash test itself, but probably would burst, I would say. there is no ultimate safety for a Type 4 cylinder. If the crash is heavy, the impact is very, very strong, then yes, it can burst. Okay.
I'm not aware of any burst, honestly, from any vehicle at all.
So
I'm not aware of that.
Yeah.
But never say never.
Right.
Look, I can just to continue that discussion. I've attended, and in one of our projects we have tested such cylinders with a with a heavy weight in a tower that fell down from 30 meters or so.
Yes.
And if that weight hits the boss, on a right like this, it's very difficult, and especially if the tank is empty. If the tank is full, it's no problem.
Yeah. I know that many people believe, well, it's a polymer, it's a plastic tank, but the properties of carbon fiber, for those who really deal with carbon fiber on a daily basis, and we do that, they know how strong this material actually is. It's absolutely amazing. Mm-hmm. It's absolutely amazing, right? And that's what I can say.
Okay. It is. So let's share a few words on those green. How did you call it? Green tanks for green products or something?
Yeah, green. The CO2 footprint of right. So yes, carbon fiber production itself is still it's energy intensive, and it uses of course not green energy or renewable energy, right? If I'm not wrong, it is said that 1 kilogram of carbon fiber under normal circumstances creates 19 or 20 kilograms of CO2. Oh, that's a lot. Okay, but that is really something that is really on the agenda of us, the clients, and the carbon fiber manufacturers. So how to get the CO2 footprint of carbon fiber down?
And what about the resin, thermoplastic resins? Is that something you're working on?
We are working on all the components that are in a Type 4 cylinder with our manufacturers. Yeah. But it's we are the client, of course. We can only talk and demand, but it's still a long way. And at the end, it's always also a question of economics, using green energy. Just right now in Europe, it gets more expensive, right?
Yeah, absolutely. Unfortunately.
Yes, unfortunately.
Unfortunately. But at some point we will get there, and I think we all agree here in this room that we shouldn't wait until everything is perfect and until all the stars, are aligned. We have to start now. And you're active on all markets, right? All over the world. India, Australia.
Yes.
South America.
Yes. Well, right now the hotspot is actually Europe. Without doubt, that's and then we see activities in of course China, but they are delayed in the introduction of Type 4. Mm-hmm. Yeah, Type 4 is still not allowed for use in China, but new standards are being written. Mm-hmm. And we hope that then finally in 2 or 3 years, the Type 4 is then allowed. Probably it will come first in the mobility and then in distribution. And then we see a bigger potential there. Korea, Japan, they are waking up. Japan and Korea, they have the vehicles, the Mirai. USA, we hope that through the IRA, the Inflation Reduction Act, that should really trigger something. Okay, But again, the constellation is different. It's more liquid than compressed, right?
But speaking about liquid, you're also invested in CryoShelter.
Yes.
So this, let's say, liquid hydrogen company in
Graz,
in Austria. Is Graz or in Austria? I'm not sure about the place anymore. So how do you see this business growing? Is it going to be a business for you?
Well, we made this investment in order to reduce risk exposure. I mean, our business is all around compressed, right? But we see that liquid tanks for heavy-duty trucks might really become or gain market share in the future, right? And that was the principal motive for the investment in CryoShelter. So if this 1 year takes off, then we have a diversified product in our product portfolio.
Okay. So it's more like risk hedging, or let's see how far it gets. But your current focus is on on
compressed,
right?
Yeah,
on compressed hydrogen. All right. So wow, we have so many questions left. My team has just posted me a link. I will share it with you. Where is it? Something's wrong with the chat today, or it looks like something's wrong. Here it is. An article a scientific article on regulations for compressed hydrogen. So maybe for those of you who think that this webinar was interesting, but you still have sleepless nights, so you can go through that scientific article afterwards. What's the typical weight ratio of your, let's say, most recent tanks in terms of weight, kilograms of hydrogen per kilogram of tank?
Yeah, I believe we are talking about 7% something. Yeah, targeting maybe going higher. Yeah, but that's a good value. Yeah.
Okay, 7%.
Yeah, a little bit more. Yeah.
Okay. Just the vessel itself, without taking all the pipes and everything into account.
Right.
Okay, so let me repeat it again. In 3 weeks, we have that webinar on hydrogen in Taiwan. If you can't read those Chinese symbols, it says CTCI Foundation. It's a research institute in Taiwan. We have 2 speakers. One of them is Harry Kuo, who's also here in the room, who is an expert on composites as well. And he asked the next questions. Are there differences in mechanical properties between Type 4 tanks made of dry winding and wet winding process?
That's I believe you can answer this better than I. I cannot answer it because yes, we made our tests, of course, because we use wet winding. Okay, but we made our tests as well with dry winding or with toe preg and different technologies. We have to say we still stick to wet winding after so many different researches that we did. But maybe you, David, you have a better answer here.
Well, you know that I'm still frustrated with this answer, but I get whenever I discuss with people, I get the same answer. Wet winding is cheaper, and that's why we do it. I personally believe, I'm not an expert for composites. I have almost 20 years of experience with hydrogen storage. In October, I will complete my 20 years. but I'm not an expert, for fibers. I just see the process of wet winding, which is difficult from a quality control perspective, which is difficult from a development perspective, which is, has some emissions from that resin. So when you go to those factories, but I've seen your new factory, which is probably the most modern factory in the world for tank Type 4 tanks.
Yes.
Absolutely amazing factory. Really fantastic place, fantastic factory. So I'm not saying I'm right. I'm just saying that I believe that if you look at it from a first principles, it should be better, but I can understand if you say that it's more expensive. We have to wait for a few more years until Topreg fibers get cheaper. Let's let's do one more question on those carbon fibers. The market is, I think, from my perspective, pretty challenging in terms of suppliers. You don't have many suppliers, or has this changed and you have like 10 suppliers which can supply the right quality of fibers for a very low price?
Oh, now I have to be careful what I say, because this is really a hot topic. There are about 15 carbon fiber suppliers in the world. Okay. And the market is dominated by the Japanese companies. I believe they have 50% overall market share. You have the usual suspects. There's Toray and Teijin, and I believe Mitsubishi. And exactly. So then you have Korean companies, and what we see right now is Chinese companies coming up, and we also see investments in new plants, for example, in China. And yes, the carbon fiber industry is, of course, for us of extreme strategic importance. No doubt about that, because that's without carbon fiber, we just would not exist. So, and we saw in the past, in fact, really ups and downs. Yeah, strong changes in carbon fiber prices, going down, going up, and so on. And because we compete with other industries, we compete with the
aerospace,
aviation industry. Yeah, so 2 or 3 big planes are now built with carbon fiber bodies. With the automotive industry, with sports goods industry, because after Corona, suddenly the sport goods industry took off like crazy. So we have now again a particular situation. I don't tell you which one it is, but we don't know whether this will last for the next 2 or 3 years like it is today, because we have seen so many changes. Okay, because the same production lines are used for all these different market applications. Okay, so but what I can say is this: we have a size as a customer that is not small anymore.
Okay.
So we are a strategic buyer for carbon fiber.
Wow. Okay, that's good to hear.
So this gives us a certain power. Okay, and to negotiate good prices, but also to secure carbon fiber. Okay, that is certainly more difficult if you do not have the volumes that we have. Okay, no doubt about that.
Okay,
but yes, we have a constant carbon fiber work group implemented in the company that has the clear focus securing carbon fiber.
Okay.
And yes, we also have double or triple supplier strategy.
Okay, yeah, makes perfect sense.
Which is not so easy, as you know, because if you change a carbon fiber on a cylinder, that means new homologation, new certification, and every fiber and every manufacturer and even every plant delivers you different quality range and tolerances and so on. So it's tricky, but for risk mitigation, you have to keep 2 or 3 suppliers.
Yeah, of course. Okay, yeah, that was a very good information, because I agree that this has always been one of the biggest challenges for not only for you but also for the other manufacturers on the market. Okay, so actually our 90 minutes are over again. Let me try to answer one question myself. Do you build hydrogen filling stations? I think that was more towards me because Hexagon doesn't build refueling stations. You just deliver the storage.
No, we do.
Sorry. Yeah. Okay.
But
the mobile ones.
The mobile ones. So we do not. They can have the same functionality, but yes, we have a product line for mobile refueling stations in our portfolio.
Okay. Yeah. Okay. So that's correct. Of course. I mean, we work with you on those.
Yeah.
But you will not implement them somewhere. So you just sell the equipment and. Because what we do, that would have been my answer. Yeah. We integrate them, so we plan them, we build them. In terms of we put them on the ground. That would be our business, but you deliver the
equipment.
The equipment.
Yeah, we support to a certain extent. For example, if the client requires some kind of specific documents for the approval, the local one, but here it ends. So we are an equipment manufacturer.
Okay, and that's so if you need something, we can't build them, all over the world. So we're with that kind of business, we are very local.
Right.
But if you're in South America or in Turkey or in somewhere else, we could deliver you a blueprint for that. So we could tell you how to do it. And Mirko, just to answer your questions, because I see that you're from a Type 1. Stationary storage manufacturer, just send me an email or send us an email, and we can talk together about your about your large, very large stationary tubes, because that's certainly not the competition of Hexagon. But Ali is happy. Mobile filling station sounds great. We'll look into these right away. Thank you again. So okay, your answer was correct. And not only your answer, the full presentation was fantastic. So let's give Hartmut a last round of virtual applause in the chat, please. And since the Olympics are still going on, I will award you a first place gold medal in the hydrogen webinar Olympics. Where is it? It's not there. I don't know what happens with my chat. So again, it's not only a virtual medal. It's it's also it's not there. I don't know why, but just look at the chat. Standing ovations at the end of this webinar again. I think I did not overpromise. I announced this quality, and you delivered this, so you even over delivered on my on the high expectations that I've set for this webinar today. So thank you very much, Hartmut. Thank you to the attendees here in this room. We have a summer break now, 2 weeks, so you can all enjoy 2 weeks of holidays without fear of missing out. I'll see you again in 3 weeks. We're in Taiwan at 10 o'clock Central European time, which is late in the afternoon or early in the evening in Asia and in Australia. And in 4 weeks, we're in Colorado again with Professor Rob Brown, our fantastic speaker that was here 2 weeks ago, last week actually, another amazing speaker on solid oxide electrolyzers, state of the art and outlook. So thanks again. And the song you will hear in a second is called Hydrogen Guy. It's available on Spotify. I want to I want you all to listen to it every day because I want to become, I don't know, the Taylor Swift of the hydrogen industry, and I want to hit the Spotify charts with that song. So I want you to listen to it. I want you to share it with your friends and with your colleagues. Thanks again. Have a nice rest of your day, and see you in 3 weeks. Bye.
Thank you. Bye.